We will now investigate the usage of Perftools-lite. Perftools-lite was developed to make it much easier for the end user to examine the performance characteristics of their application. It is extremely easy to use. The only thing required is that you load a couple modules prior to building your application. The first module is Perftools Base. This module actually needs to be loaded regardless of what version of Perftools you use. And then you load Perftools-lite. Now we are going to make the application. This is a very interesting application. It's an astrophysics code developed at North Carolina State University. It's relatively small, but it has some very interesting performance issues. Now, as you can see, when you use Perftools-lite, you get a message at the end of the build that it created a Cray instrumented executable called VH1. And that is what we're going to run. Now, those of you who are used to using the Perftools module without the lite would now have to do something like do a pat build and then execute and then do a pat report. But now all we are going to do, if we look at our script, is we're going to run on 8 nodes, and each MPI task, of which there are 64, will have 4 threads. And there are 8 MPI tasks on each node. We put 4 on each socket, so we are balanced across the 2 sockets. Okay, now we simply do a Q-sub of run it, and we get our job name here. And now if we look at our output, hasn't started yet. There's our execute. Notice these .lst files. This is from using the -hlist equal a. And you'll see how those are very useful once we start looking at our statistics. Okay, so now what we see is it is running. VH1 outputs its output into a directory called output, and Perftools puts its statistics into a directory, and it gives it a unique name. Okay, and it is finished. So this is the output, and so now let's examine this output. And what we see, this is the start of the program. Cray always puts out a banner saying what version is being used and the date, etc. And now basically this is the output from VH1. It was only run for 10 time steps, and it ran for 28 minutes. Now, after the output from the application, which in most applications would have much more than that, we get the Cray lite performance statistics. It gives us the version again. This is when it was built in August 22nd. The experiment is a sampling profile. This is the number of MPI ranks. This is the number of MPI ranks per node, and the number of threads per MPI rank, and the number of cores per socket. Now, it turns out that this Broadwell has 44 cores, and and this is the system name and the hardware that we're running on. Then after we get that information, this is the average process time. All of these statistics are averaged over the 64 MPI tasks. The high memory mark, once again average, and the memory per PE. Then the megaflops and the megaflop per second for each PE. The I/O read-write, the I/O write rate, and the energy consumed per node in the watts per node. Then we have the traditional profile. As we see here, the user routines only use 58.9% of the wall clock time. MPI uses 36.3%. Etc. are system routines. Now, the only thing that is displayed is those things that use more than 1% of the time. This, once again, this sampling is a sample every 100th of a second, so it ran 28 seconds. This is the load imbalance. And you can see we really have significant load imbalance in these routines. Now, a lot of that load imbalance is going to show up in MPI. The problem with this and sampling, you cannot split out the MPI sync time, which would be the time for all the MPI tasks to arrive at the all-to-all, from the actual execution of the all-to-all. And I'll show you how we can get that in a future video. Then we go down to a finer level. As you can see here, this is the routine that uses the most time. Now, all of these samples are exclusive. In other words, they're the amount of samples obtained in that routine, excluding routines that it calls. And this gives you the line numbers that are using most of the time. Now let's look at one of those listing files. In particular, we're going to look at parabola LST. And we want to look at line 32, 45, and 86. So let's look at 32. Now what this is showing us is this do loop has been vectorized, it has been unrolled by 2, and it's been fused with the preceding loop. This loop has also been fused, so these 3 loops are actually now all in the one loop that goes from this to this, and this one is a special case to merge in. Now this loop is not merged, and so down below we might have some others merging. Let's look. And sure enough, you can see how this is fused, and so we have some good fusion going on here. Okay, so you can see a lot of those, and down at the bottom of the listing it gives you a summary of what lines are vectorized, unrolled, etc. Okay, so let's go back to our profile, and let's look at one of these OpenMP loops. So we're going to look at sweepy.y.lst. Whoop. Okay, and as you can see here, this is the OpenMP loop. It is designated by a capital M, which stands for multitasking. And this is the streamed loop. This is the OpenMP loop. When you just have a number on the, that means nothing was really done with this. This particular loop was unrolled by 8. The reason it unrolled this instead of vectorizing it, because notice that there's a significant stride here. This array is accessed on the 3rd dimension, which basically is going to stride through this array the product of these inner 2 dimensions, which would not give us good vectorization. So it's unrolled by 3. This is vectorized, and you can see that there is a call to ppmlr, and then another vectorized loop. Now this call chain going down through this routine is what uses the routines that we saw in that profile. This is a fairly deep call chain. Here again, this is packing up a buffer, and it's unrolled by 8 because once again we're striding on J here. And then we have the MPI all-to-all. Okay, so let's go back to the profile. All right, and as you can see, once again, the only thing that's shown here are those things that use more than 1% of the time. And then we get information on the files that are read, and then information on files that are written, and some information on the Lustre file system that was used. So that gives us some pretty good information. Notice that we see that there are some suggested PAT reports that we can run now. Let's investigate some of those. So we'll get out of this, and now we're going to do a PAT report. And one of the displays I really like a great deal is the call tree. And that's what CT stands for. So I'm going to put this into a file called profile call tree. All right, and now we can look at that. All right, here again, this gives us the information that we had on the previous report. And now we come down, and it also, so it tells us what we ran. And one thing that I should point out here, the default is that it's going to just give you the average. If you would like to get information about all of the threads or all of the MPI tasks, now this would be a lot of output. You could replace hide with all, or you could also use min, max, average. But this call tree is excellent. So this shows you the execution of the program. It starts VH1. Now, one would think that it calls S-sweep Z first, but that's not how this call tree is displayed. What it shows you is this is level 2 in the call tree, and it shows you which level 2 path uses the most time. And this shows you that sweep Z comes in, and there is an all-to-all. That here again, this all-to-all is before the OpenMP region because it uses more time. And then it goes down, and this shows you this call tree I was talking about. Here's the call to PPMLR, which calls remap, which calls parabola, and then this is the amount of time used in relap exclusive of parabola. And then it calls PPMLR, then calls Riemann and parabola again. And then we come back into sweep Z. So this is, and as you can see, these routines that were listed as high compute in the first profile are really using a lot of, are being called from these OpenMP loops. And here's now another OpenMP loop in sweep Y. And it also has MPI all-to-all. Here again, this is level 2. And this is level 3. So everything between here and here, which is another level 2. There are 2 bars. There's not a 2 there. Is contained within that level 2. So this is just an excellent way of looking at that. Now there is another display that's kind of interesting, and that is callers. Okay, callers is kind of the reverse to call tree. It's bottom up instead of top down. So let's look at profile CA. And now you see that the routine that uses most of the time is parabola. And then it shows you the callers that account for this time. So parabola is called from remap, which is called from PPMLR. And when called from PPMLR from sweep Z, it uses 2.7% of the time. Sweep Y, 2.5, sweep X2, 1.3, sweep X1, 1.3. Now notice that there's some more down here. This is level 3, where PPMLR calls remap that calls parabola. But it turns out that PPMLR also calls parabola directly. Okay, and then PPMLR is called also from these 4 routines, but since some of them are less than 1%, they're not being shown. And then Riemann is being called from these 4 OpenMP loops, as you can see. And also we have higher up call trees. So those are 2 of the displays that I think are extremely helpful in really finding out the execution pattern of your program. Okay. Now, that concludes our discussion of Perftools-lite. The one thing that we are missing here that is very important is loop statistics. And the next video will cover Perftools-lite loops that gives us that information. Thank you for your attention, and I hope this was helpful.